We just had the Barnesburg time trial here, May 2013, and we had a lot of wind, so I thought it'd be a good time to talk about the physics and mathematics of wind. When we ride, we all feel a force exerted against us by the air. That force is equal to this constant gamma. I'll explain what gamma is here in a minute, times the frontal area of the cyclist, times the velocity of the rider squared, and sorry, there's a 1/2 right there in front. Now, these three terms right here, this gamma is has to do with barometric pressure, density of air, temperature of air, etc. It's a very small number, and it's a constant, and we looked those up in various manuals of earth materials and stuff like that, but it's basically, for this discussion, not important. Neither is the area, the frontal area of a cyclist, the area that is exposed to the wind, to the air as we move. The term we really want to think about here in terms of the force, I think, is this as velocity, our speed into the wind. Okay, so what we're going to do is we're going to take these right here and we're going to throw those out for this discussion, okay? And we're going to talk about force as a function of our velocity. Now, we know that we have both headwinds and we have tailwinds. And we all know that it is much easier to ride in a tailwind than a headwind. Well, as it turns out, it's a whole lot easier than you think, even mathematically. Let's take this velocity term here. Of course, the force acting against us in the air is equal to our velocity into the air, and it's also equal to plus or minus the wind. Okay, plus and minus here would be a direction, and then that whole term there is squared. Now, for the case where we have a headwind, that would be velocity plus wind. That would be our actual speed through the air. And in the case of a tailwind, we would have our velocity minus the wind, and then that quantity is squared. I want you to look at what happens when we expand these terms. We have the rider's velocity plus wind, and since that's squared, we have another term just like it. And we don't end up with v squared plus w squared. We end up with v squared plus 2vw plus w squared in that case. So there's a whole lot more to it. This middle term right here really gets you. It'll really slow you down a whole lot more than you think. All right, likewise, this term over here, in case with a tailwind, we have the velocity of the rider minus the wind, and we have that term again because the term is squared, okay? All right, so when we expand that, likewise, we get velocity squared minus 2 velocity times the wind, and then we have plus the wind squared. Negative w times negative w is positive w squared, okay? All right, so there's our two relationships here. Let me do a little erasing here. I've got this term and this term, okay? One for headwind, one for tailwind. Gosh, I'm making a big mess here. All right. Could have thought ahead and gotten a rag, but I didn't. All right. This right here is for headwind. We'll just call it H, and tailwind for tail, okay? All right, now let's look at this. Let's suppose that our velocity is 20 miles per hour, okay? And let's say that the wind is 10 miles an hour. All right, for the case for a headwind, that would be 20, okay? V plus 2VW plus W squared. So 20 squared plus 2 times 20 times 10 plus 10 squared, all right? 20 squared, 400. 2 times 20, 40 times 10, another 400. And then 10 squared, 100. So in the case of a headwind, we end up with 400 plus 400, 800 plus 100, 900. Okay. Units don't really matter here. We're just talking about magnitude. Remember, we threw it away part of the formula, so we're just talking about magnitude, and we're going to compare a headwind, which has a magnitude of 900, with a tailwind, which is going to have, we're going to compute that right now. All right, let's just do it right here. Velocity we said was 20. We're going to square that. Minus 2 times 20 times 10, and then plus 10 squared. Okay? So 20 squared, 400. 2 times 20 times 10, 400. Plus 10 squared, 100. All right. So the 400s cancel out, and we have a magnitude with a tailwind of only 100. All right, so what does that mean? Let's just get us a box up here. What does this space mean? Okay, in our case that we set up, the headwind has a magnitude of 900, brings to this equation here, value of 900. Again, units don't matter because we're talking about magnitude. The magnitude of the headwind and tailwind as it goes into this function here, the force function. We came up with a tailwind of 100. Okay, so in the case for Barnesburg time trial the other night, you took off into a tailwind. So, and you know, you could have been running 20, 25, 30, 35, and then other places, you know, 5, 10. But basically, you know, 20 miles an hour is a good relatable number. And then a 10 mile an hour wind with, you know, gusts of 15 to 20. But look at the magnitude of the headwind is 9 times what the force against you is bringing to bear on you in this force function. 9 times that of a tailwind. So you can see it's not a direct relationship. So when you're right out there, the air movement is having an impact on you with a magnitude of 100. When you flip around and come back, that 100 now becomes 900. And it's the very same wind. Wind did not change speed, still 10 miles an hour. So that's why we feel so much better in a tailwind than we do a headwind. And aerodynamics is so important in cycling because these values are not linear. In other words, it's not just velocity and wind. It's velocity and wind squared. And when you put those two terms together in the additive or subtraction kind of scenario, they get squared, and then they have to expand in a binomial format, okay? This binomial expansion here that we saw. So we end up with these extraordinarily differing magnitudes. And I hope that clears that up a little bit for you. Hope you enjoy the video. And you don't have to be able to follow the math. Just realize that we've demonstrated headwinds. Direct headwinds, direct tailwinds can have as much as, 9, 12, 15 times, depending on our velocity and the velocity of the winds. All right, thank you very much.